2000s, GM stopped their electric car project. They weren't cool. In comes Tesla, who made the electric car a popular concept. But is the cool factor the biggest factor in electric car sales these days? Are electric cars actually better for the environment, and do the majority of buyers really care? Brandon and Rich debate the subject and more in this edition of the Embedded Insiders. Later, the Insiders are joined by Frede Blaabjerg, an esteemed professor of power electronics and drives at Aalborg University in Denmark. The three discuss the current state of the power industry and what the future looks like. Power will play a big role in the electric vehicle industry, but just how big?
Welcome to another edition of the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and I'm here with Rich Nass, who is, what are you going to be this time, Rich? We've had you be Darth Vader.
Well, this was a long week. We had our OSM summit this week where we normally gather the entire company in Scottsdale for a week of stuff. But since we don't travel right now, we did it virtually. It was actually, I'm derailing the conversation, but this is sort of important. We had everybody on a virtual call, and it actually worked out really well. I won't say my expectations were too low, but I was very pleasantly surprised at how well the virtual meeting was able to take place with everybody participating and everybody paying attention.
Well, if I'm going to give you a title, I guess then that means you're the czar of Zoom. But I thought it went really well. You know, it's obviously different, and there's a lot of benefit to being in the same physical space as your colleagues. But, you know, given the circumstances, I don't think it could have gone much better.
Yeah, and in the next month or so, we'll roll out some of the ideas that we talked about to the audience, because I think there's some really exciting stuff.
For sure. Speaking of exciting stuff, we had a story up on Embedded Computing Design that talked about the invention of Tesla's Model S. And it was surprising that Tesla as a company started way back in the early 2000s. And it was actually started based on the fact that GM had killed an electric vehicle that they were working on. And part of the reason that that vehicle was killed is that nobody was buying them, because if you remember back in the 90s and early 2000s, and even still up until today, a lot of electric vehicles looked like weird space nerdy cars. And Tesla,
yeah, but that particular one that GM killed did not look like a weird nerdy car. It was the Chevy Volt, if I remember right. And it looked like a regular car. I don't understand why it didn't sell.
Oh, I think it looked weird. I wouldn't have bought it.
But it might have something to do with the price tag.
But Tesla has made electric vehicles cool, which is really important. And the other important thing is, like you said, the cost. Over time, Tesla's tried to make cheaper and cheaper versions of its vehicles. And, you know, they haven't been completely successful, but on the whole, the affordability of electric vehicles has come down significantly, which is great for the environment because electric vehicles are so much cleaner than the alternative.
Well, they've made them cool. They also made them very well. That's a car that drives really nicely on the road. However, since I'm supposed to play devil's advocate here, if you chart out all this stuff, you actually use more natural resources to build an electric car than you burn in a regular gasoline-powered car. I'm sure you knew that.
Well, you know, the truth is that over the lifetime of an electric vehicle, it is still cleaner than an internal combustion based vehicle.
I didn't say not cleaner. I said the cost of natural resources.
The cost of natural resources to support the battery, that is definitely true. That there's no disputing that whatsoever. And actually, the process of harvesting that material is very detrimental to the environment. You like twice as bad as just producing a normal vehicle. But when you factor in the savings that you get from the time that thing hits the street to the time that it's taken to the salvage yard, overall, with the production included, it is a cleaner alternative.
But the other unknown there is that there's not really any historical data, because these automobiles haven't been around long enough to even know how long they're going to last. Will there be a car in, one of these cars in 30 years? Will they still be on the road? You just have to swap out new batteries and it runs fine. We don't know that. And with automobiles, they've been around since, I don't know, about 100 years or so. So there's plenty of historical data.
An electric vehicles have been around for a long, long time. It's just that the major auto manufacturers have sort of killed them because it would have cost them a ton of money to implement them. But you're right. They haven't been around in the scale to have significant, worthwhile test data. So it's going to be interesting over the next 5 to 10 years. I think 500,000 Teslas have sold to this point or something like that. It's going to be interesting over the next 10 to 15 to 20 years to see how that plays out, because to your point, some of these power electronics, the components, the batteries, etc., they are just by default going to degrade over time. Their efficiency isn't going to be what it was, in year 10 as in year 15 or year 20, right? So we'll see what happens. And then, of course, there's the other thing. What do you end up doing with all those lithium batteries, right?
And if you're a conspiracy theory guy, is it the oil companies that are putting the kibosh on the electric cars?
It is. Damn Halliburton. But
what can we do to make these cars better, Brandon?
That's a really interesting question. And I think a lot of it has to do with a big debate that's been going on in the power electronics industry for a while, is these new materials that can be used. We've heard a lot about gallium nitride and silicon carbide over the last few years. Actually, it's been more than a few years now, but they're really starting to fall into place and become mature enough to be deployed at large scale and in sort of general purpose applications. So hopefully those will tip the scales. It's really a cool way to see how everything comes together when you start thinking about our space and what we cover in terms of these components and how they could really end up making an impact on the environment and the cost of you and me buying cars in the next 5 to 10 years, etc.
Before we get into the real design of these things, the other practical part of this is that who fixes these electric cars? You're not going to go to Joe Mechanic anymore when you need there is no carburetor, for example, and a lot of the traditional parts just aren't there. I guess you go back to the dealer to get it fixed, but that's a different problem.
Yeah, I think that was one of the big things that Tesla struggled with early on and still does, is that in order for somebody to get their Tesla service, they'd have to go back to Tesla. There isn't that aftermarket, of mechanics yet. There are some of them, but they're not as widespread as, like you said, your traditional Jiffy Lube, right? You just go down and get the oil changed and have them take a look at your air filter. So that's going to be something that over time is going to have to expand, just like, the gas station pumps are going to have to start supporting electricity and so on and so forth.
Now, the insiders are joined by Frede Blaabjerg, professor of power electronics and drives at Aalborg University in Denmark.
The power industry moves slowly. We had a little debate about why it moves slowly, though. I think it has more, I won't say marketing issues, but less technical issue that power is mission critical in almost all the times that it's used. In the car, in high power places. And if there were to be a failure, people's lives are at stake. And so for a lot of good reasons, it really has to work all the time, every time. And that's why I think that the power industry moves slower. Brandon seems to think it's more of a technology issue.
So Freddie, silicon MOSFETs have been the material, at least du jour, for a long time now in the power industry. Do you think that some of the reasons that it's slower to move is that once you get onto a material, it really becomes limitations of that material, and that once you've selected that material and you've gotten the production and the scale to get that out into the market, that you're really just dealing with optimization at that point?
Yeah, I think that's right. If we discuss the silicon technology, MOSFET technology for different applications, IGBT technology for more industrial applications and so on, you can see that the improvements are more incremental. And some of the main reasons are for sure that the investment you have to do in order to provide devices, components, and also systems, they are huge. and you want to pay off such kind of equipment and also facilities you have investment in. That's a fair way to look at it.
So where do the wide band gaps fit in? We've heard a lot over the last few years about silicon carbide and gallium nitride. How are they flipping this equation upside down? What do they offer that silicon MOSFETs don't?
The power electronics field, it has been known for decades that there was possibilities to apply other material than just silicon for doing power devices. One of them is silicon carbide, another one is gallium nitride, which have a much better characteristic in terms of doing the main thing the power devices have to do, and that are to turn on and turn off very fast in order to do, for example, switch mode power supplies. Let's say in the last 20 years, we have come closer and closer to being able to use this technology. The first thing coming up was the diodes. Silicon carbide based diode already around 2000 was possible to do this to a reasonable price. But in the last 5 years, the technology has moved so fast that we see more and more emerging and possible application of wide bandgap devices. And those wide bandgap devices, seen from their potential merits, they are fantastic. Because they can do the work silicon do maybe 10 times faster. On top of that, they are also having much less losses. So it becomes more and more obvious that this is going to be a main trend in the future for the power conversion.
We've been hearing about the battle between these two technologies for quite some time now. So my question is it really this battle, or is this something that's made up by the media? Are we part of that media? I guess we are. Is this something that we're making up? And does the industry really understand what the difference is between them and where their places are? Or is it competitive?
The technology has its merits dependent on voltage level for the moment. There is no doubt that some kind of development can be done. So let's say the technology is going both in each direction. So the gallium nitride components, they are most feasible at low voltage, but high current. So that means computers, power supplies, automotive, other applications where it's interesting. If you take the silicon carbide devices, they have fantastic capability in terms also to go up in voltage about 1 kilovolt. And in that respect, gallium nitride is not so easy to do yet at a high level of reliability. So in this area, 1 kilovolt and below, let's say 500 volt, 400 volt, you can call it a battle, but we can also see an area of possibilities, because seen from a supplier of products, it's a fantastic opportunity that now you have two different technologies to select between when you are going to come with products in an area where a lot of application is. So seen from the application perspective, it's a battle, yes, but it's also a possibility, because instead of just having one technology option, you have two technology options, and you can look at what fits you best in terms of manufacturing.
At this point then, Frede, what are the major technical challenges, if any, that are left in bringing these more into the mainstream?
A lot of things are bottom line driven by cost. So if the technology is still relatively expensive to manufacture, then you can say that you have to come up with better ideas about lowering the cost of manufacturing of those devices. And this is still kind of barrier for the technology. They are been working a lot in terms of, let's say, making the manufacturing more streamlined, larger scale. One of the issues is that the yield is not high enough in order to come further down in price and so on. So there are a number of important steps to be taken in order to make it cost competitive. And then it is always so with new technology that new technology is evolving year by year. Then there are also larger uncertainties if we look from the market perspective, not as the end user like you and me when we buy a computer or we buy a charger or we buy a car or so on, but for sure for the manufacturer and the user of the components to put into the products. They want to be sure that they have a technology which is mature enough in order to put it into, let's say, mainstream products, and they are not having a risk of certain unexpected failures if you do not have enough experience with the components.
So from a developer standpoint, how are the advent of these technologies into their designs, hopefully increasingly over the next several years, going to change the way they work? Are there, are new tools going to be needed, or new topologies going to be needed? How, does your board layout change? What's different for the designer?
I have to say we have to really re-engineer all the design. So there are a lot of things to be looked at. The advantage immediately is that the losses are just, let's say, for the same power, 1/10, also you,
Wow.
and maybe 1/5 or something like that. So that means that now you are dealing with much more power in the same volume or with the same weight. So the cooling will be reduced. That's of course an advantage, but that also means that you really make things much smaller. And you have to have connection into the box and you have to have connection out of the box, and typically they are not changed. So the area you need to do things around will be much smaller. And what you further see is that you are operating with very high change of voltage, very high change of current. And we all know if they are very high, then we also have a high risk of interference, of noise. So that means your circuit layout, your integration have to be able to really ensure that you do not have a very good radio amplifier or something like that. So the design, in order to be able to deal with such fast devices, will also be completely different. So the designers, the power electronic designers, I would say they really have to step up in terms of to do very good circuit layout. But if they're able to do that, then they also get fantastic equipment out of it with spec marks, which we have dreamed about for a long time. And the capacity per volume, the capacity per weight is really looking fantastic on many different demonstrators we have around the world.
Are there even power analysis tools right now that are available on the market that are optimized or extremely efficient in dealing with these types of devices?
Well, I would say the models, in order to do simulation of the components, they are available. Such things have been done, so they are also implemented in SPICE-like tools or something like that. In terms of simulating, let's say, quite advanced structures, also the cooling system and how the heat is distributed in a package or something like that. They are also relatively good tools which we can transfer from the silicon domain into the wide bandgap domain. But there is no doubt as we are switching much faster, especially the EMI is an issue of concern, and we have to study this much more carefully compared with what we needed to do in terms of doing the silicon products.
What do you think that these technologies mean for applications that have been on the brink forever? We've been talking about widespread renewables forever. We've been talking about electric vehicles forever. Is this sort of the tipping point where we now go, okay, we can do this much more efficiently at scale at cost points that are reasonable to really flood the market with clean energy?
Yeah, so that is what we, let's say, the transportation is a commodity. I would say the transportation is first now really becoming electrified, right? And this is now in some countries going with a very rapid pace. For example, one of the manufacturers of electrical cars, as a fully electrical cars, who are applying silicon carbide in their drivetrain, and there are also others who are looking at it. So there are predictions that by introducing silicon carbide technology in electrical vehicles, the range will maybe be increased by 5 to 10%. And if you have such kind of benefits, that will obviously be an advantage. In terms of renewable generation, which is also a very booming application, I would say that we have two main sources. One is photovoltaics, right? And the second one is wind. The wind, this is really large power where we see the absolute dominated market. And I would say it will take some years before we will see the silicon carbide technology be applied for this very large scale power as a standard in the product, but we will see some first iterations on applying that in the near future. If we look at the photovoltaic area, there we have different groups or classes of power. So we have the one inverter per panel, right? This is the module integrated inverters. There I would expect to see relatively fast gallium nitride to be a part of some of the products. Then we have the string inverters up to 10, 20 kilowatt and so on. We could also see silicon carbide, maybe gallium nitride being a part of that. While for the central inverters where we are in the megawatt, it's a little bit aligned with the technology we have in the wind turbines. That being said, the diodes which are applied also in, for example, in wind turbines could be silicon carbide, because this is really a commodity in terms of technology, and it's relatively cheap. So a combination of a silicon-based transistor and silicon carbide-based diodes will be seen and can be seen in different applications.
So 5 to 10 years from now, what do you think the market looks like? Are we completely dominated by wide band gaps?
I love when we put people on the spot.
Not
like that.
100% for sure, but there's no doubt that the wide bandgap devices, they look into a 2-digit growth per year. So in 10 years, a little bit dependent on the electrical vehicles, because this is a so big market. If that's coming, this is much bigger than what we see today of the total electronics market. So if that is coming, then it will be a little bit dependent on what is developed for that. But no doubt 20, 25, 30% of all power electronic products, they will be based on wide bandgap devices in 10 years.
Thanks for listening to this edition of Embedded Insiders. For daily industry news, videos, and podcasts, visit our website, embeddedcomputing.com.